So yeah, I don't mind if I'm giving you an overestimate of how long it takes, that's fine. All right, so let me share my answers to the quantitative ones. We'll do those first, and then we can talk about the qualitative ones after. For number 2, I found that the electric field strength was 3.0 times 10 to the 6th newtons per coulomb to the left. Just write these down. Now, I am happy to talk about the direction for all of these. But I really don't want to look at the math for more than 1 or 2 of these. For number 9, I found that the charge that was creating the field was negative 1.25 times 10 to the negative 8th coulombs. For number 12, I found that the electric field strength was 6.25 times 10 to the 4th newtons per coulomb, and that was to the east. And then for number 69, for part A, I said that I actually don't remember what the question was, but I said for B, I found that the force exerted on the electron by the electric field was 2.4 times 10 to the negative 17th newtons up. And for C, I found that the gravitational force that the Earth was pulling on the electron with was 8.9 times 10 to the negative 30th newtons, and that was down. All right, so again, I'm happy to talk about the direction for any of these, but please raise your hand if you need help with the math for number 2. Okay, nobody. Raise your hand if you want to talk about the direction for the how about number 9? Wow, that makes me think. Is it just a negative sign we can talk about? No? Okay, interesting. How about the math for number 12? What about the direction for number 12? All right, how about 69A, that's up? I don't remember what the question was, yeah. How about part, it looked like you did pretty well in this. Part B, anybody see the math for that? Good. And then C, some of you just didn't bother to look up the mass of the Earth or the radius of the Earth. Besides that, raise your hand again if you actually need to see that still. Okay.
Wait, why would you need to besides that?
Yeah, I mean, I'll touch upon everything that had a vote. I'm probably not going to do the entire solution for the ones that only had 1 vote, but I'll touch upon it. All right, so the first thing that we kind of needed to see was the direction for number 2. What page is that? What is it? 516? No, it's not 516. 560? 565. All right, 565. So number 2, we have a negative charge that experiences a force to the right in an electric field. What are the field's magnitude and direction at that location? So there are 2 different ways I think we could approach this one. One way to approach it is that the direction of an electric field is defined as the direction that a positive test charge would be forced. So if we have a positive test charge, the direction of the field and the direction of the force 100% of the time are the same. If we have a negative charge that we're placing in the field, then the direction of the field and the direction of the force would be opposite, because the negative charge would get forced in the opposite direction as the positive charge. So that's one way to think about it. The other way to think about it is, all right, I got a negative charge that's being forced to the right. Now there's really only 2 different types of regions of space that can do that. One would be a positively charged region of space, which produces an outward electric field. And one would be a negatively charged region of space, which does an inward pointing field. Okay, so those are the really only 2 possibilities. And again, we have a negative charge that has to get forced to the right. So I'd like you to take 10 seconds when you're done sneezing and decide where we would have to place this negative charge in this field to get forced to the right? So this is individual right now. 10 seconds, where do we place the negative charge so that it gets forced to the right? It's individual right now. Alright, which way? Or where do we put it? Over here? This is what you mean by to the left? That makes sense, because a negative charge is attracted to this positive charge. So the force is to the right, but the field points to the left, because the field is defined as the direction that a positive charge would be forced. Okay, so in this instance, the field points to the left. And then take 5 seconds this time. Where would we have to place our negative charge to be forced to the right by this electric field? Okay, where do I have to place it? I have to place it to the right because the negative charge is going to be repelled by this negative charge that is producing this electric field. And the electric field there points to the left as well. Alright? So it's not really two different ways of answering it, it's two different flavors of thinking about it. But either way we think about it, the negative charge, if it's getting forced to the right, has to be in a field that points to the left. Follow-up issues about the field has to point to the left so that this negative charge feels a force to the right. Alright, it's backwards for negative charges, it's all built around positive charges. Alright, we did want to see my work for number 9, and there were so many of you that raised your hands for that, that I just kind of wonder if I have a mistake. So number 9, that's on page 566. We're told that the electric field that's 0.25 meters from a small sphere is 450 newtons per coulomb toward the sphere. What is the charge on the sphere? Alright, so I am going to draw the electric field for my step 1. We know we have a sphere, and we know that the electric field points towards the sphere. Okay, so the electric field is like this. The only kind of thing that would have an electric field that looks like that would be if that sphere is negatively charged, right? Then the positive test charges are attracted to it. So right off the bat, I knew that my sphere had a negative net charge. Follow-up questions for anybody about knowing that since the field points in, that the region of space is negatively charged. Okay, and then for step 2, we know that we're testing the field 0.25 meters from the sphere, and that the field strength at that location is 450 newtons per coulomb, and we want to know the charge on the sphere. Questions from anybody about my step 2 or step 3? Alright, so I only know one equation, or at least there's only one equation on your equation sheet with electric field on it. And we can't use it because we don't know the force, and we actually don't know the charge on the test charge either. So we are going to have to substitute in Coulomb's law into our electric field expression. Okay, so the electric field strength would be K, QA, QB over R squared, all over Q prime, which is the test charge. So the Q prime cancels out one of the Q's from Coulomb's law. I'm going to cancel out QB. And then what's left, the QA, is the charge that's creating the field. Right? We've canceled out the test charge, so it's the charge creating the field. So I'm going to get rid of the subscript of A, and I don't think I did it last time. I'm going to replace the QA with a big Q to just further differentiate that that is the large charge that's creating the field. All right, and now I think I can solve for Q. So I'm going to manipulate my equation, so I'm isolating that. So I have to multiply both sides by R squared and divide both sides by K. So, oops, wrong thing. So the electric field strength is the 450. R is 0.25, and that has to get squared. And then K is the 9.0 times 10 to the 9th. Now, I still think I did something wrong since so many of you raised your hand. I did forget to square my R. I can see it right in my work. I didn't carry down the square. So thank you for those of you that raised your hands. The Q is going to be kind of smaller than I gave you, I think. So 450 times 0.25 squared divided by 9 times 10 to the 9th. Yeah, I'm getting, oh, actually I'm getting a little smaller. So 3.1 times 10 to the negative 9th. Then it's negative, we knew that already. So great, good call on so many of you raising your hands for that. Okay, other questions about the solution for number 2? Alright, so next we needed, that wasn't 2, that was 9. Next we had one person that wanted to see work for 12. I'll do a few snippets for that, but I'm not going to do the whole thing. For 12, we were looking for the electric field strength, and we did know the force exerted on the test charge, and we needed the magnitude of the test charge itself. So there probably was a calculator error on that one. So 1.5 times 10 to the negative 3rd divided by 2.4 times 10 to the negative 8th. So we should get that when we do that. And then to the east, one person wanted to talk about that. We have a positive test charge that's getting forced to the east. Right? So a positive test charge, the direction of the force and the direction of the field are always going to be the same thing. And then 69, I had one person that wanted to talk about part A, and then we needed a couple of pointers for B and C as well. So in 69 we have an electric field in the atmosphere that's 150 newtons per coulomb downward. What is the direction of the force on a negatively charged particle? So because we have a negatively charged particle, the direction of the force is going to be opposite the direction of the field. Alright? So just like we talked about for the other directional questions. For part B, we had to find the force that was exerted, the electric force that was exerted by the field on that charge. So I did use our standard electric field expression, but I isolated for force. So I used the 150 Newton per Coulomb field, and I think it said it was an electron, right? Well, yeah, it says find the electric force on an electron with charge negative 1.6 times 10 to the negative 19 coulombs, so that's what I used there. Again, probably a calculator issue because we just have two pretty straightforward things we're multiplying together. And then for C, I was fairly pleased with how we did for this, but we were asked to compare the force that we got in B with the force of gravity on that same electron. So the expectation here is that we were using the law of universal gravitation to find the force that the Earth is pulling on the electron with. So yeah, it's been a while since we've used the law of universal gravitation, but that doesn't mean we can just say, oh, I forget how to do it. One of these masses is the mass of the Earth, which we can look up in the textbook. It's 5.98 times 10 to the 24th. The mass of the electron they gave you in the problem. Sorry, I ran out of room. 9.1 times 10 to the negative 31 newtons. And then the radius of the Earth, we can again look up in the book, 6.38 times 10 to the 6th, that gets squared. And I got 8.9 times 10 to the negative 30th newtons. That's down. Did I forget to square again? I'm getting the hands. Yeah, Emma.
Oh, I used a different equation. I used force equals mass acceleration.
It's probably okay. Hold on a second. Hi, David.
That's what I
She is not. Okay, go back. So yeah, you could use 9.81. I mean, yeah, that's fine. Same thing, Burton? Yeah. But what I want you guys to appreciate is that we have 10 to the negative 30th newtons for the gravitational force. We had 10 to the negative 17th newtons for the electric force, and that was with a pretty weak electric field. Right? This electric force is way larger than the gravitational force. Unless we have two really massive things. Alright, other questions about 69 before we move on to the other qualitative ones? Alright, so we still have what? Well, we have 43, which is on the same page, so let's do that first. So 43 wanted to know what the two properties that a test charge must have are. That's pretty straightforward. We said it in class. It's got to be positive, and it's got to have a very small amount of charge on it. And then the other qualitative questions we had were back earlier in the chapter on page 568. So we had number 11. Right? Suppose you're asked to measure the electric field in space. How do you detect the field at a point? Let me hear from some of you guys on that. So, Sophie, what did you say for that part? You're going to have to put a charge there. Absolutely, you're going to have to put a charge there. And, if you know how much charge is on that charge and you can measure how much force is on it, then you can calculate the field, sure. So that's how we would determine the magnitude of the field. How do you choose the magnitude of the test charge? Well, we'd want as small of a charge as possible, so if we had access to single protons, that would be perfect. What do you do next? We probably end up needing to measure the acceleration. I don't know how we measure the force directly, but I suppose we can measure the acceleration and then multiply that by the mass of our test charge. I don't know, something like that. Any other thoughts about 11 anybody wants to share or ask about? There's a lot in there. Shruti?
For 11D, I said the direction.
D was the last part?
Yeah.
What do you do next?
Yeah.
Okay, what did you say?
I said measuring the direction of
Measure the direction of the force. Yeah, that's fine. Yeah, right. So, yeah, that's a weird thing to ask. All right, and then we had 13 and 14 on that page too. So 13, we're supposed to look at these figures on the top of the page. And then we're asked, can you tell which charges are positive and which are negative in those pictures up there? So Alex, what did you say for that first part?
I said that you can only tell if they're opposite direction.
Yeah, I agree. There's no arrows on the field lines or on those kind of accumulations of, I don't know what those bottom pictures are. There's no arrows. So I agree. We can't tell what's positive, what's negative, but we can tell if there are similar or dissimilar charges. And then what would you add to complete the field lines? I think that would have to be arrows. Yeah. Victoria?
I was just wondering, it sounded like the description of the picture something about being positive, so how do you use that?
It said, what did it say? Lines of force between unlike charges and between like charges describe the behavior of a positively charged object in a field. No, that's referring to the test charge being positive. Yeah, so I don't think we can imply anything about the charges producing the field. Other questions on the homework? I actually don't close the book. Other questions on the homework though? Yeah, Bert.
Not one question. For positive test charges in the electric field, is this just like a regularity, or is this like a stable law? It always has to, that field lines have to always point the way that positive charge goes, or is this only
It's only a law because we said that we're always going to do it that way.
it's like this is throughout the argument.
It's consistent throughout everybody that does physics on the planet. Yeah. So, but it is arbitrary in that we could have done the opposite rule, but we didn't. All right. So what I'd like to do before we move on is discuss those electric fields from that last homework question a little bit more. Because we only looked at 2 examples of depicting electric fields last class. And I think we need to get a couple, one notch more complicated under our belts. Let me turn the projector off first. So what we saw for one of those 2 diagrams on the homework was opposite charges sort of close to each other. Sometimes we call this like a dipole because we have one type of charge on one side, one type of charge on the other side. It's kind of like poles. And I think we should be able to sketch the electric field that would exist in the space in between and then outside of those charges. And the way we would go about doing that is very similar to last time, right? We can imagine what direction a test charge would be forced, but we have to do it twice, no matter where we put it. We have to do it for what the field from this thing would do to it, and what the field from this thing would do to it. And any place that we drop a test charge directly in between the 2, right, is pretty straightforward, because the positive charge over here would repel it, and the negative charge over here would attract it. So like on this test charge here, the positive one is going to push it really strongly to the right, the negative one is going to push it pretty weakly to the right because it's so much further away. But the important thing is that those two forces would add to each other anywhere along that line that connects the two. So we would absolutely, and I think this should go in your note, we would absolutely have a field line that goes straight from the positive to the negative. So let me give you guys 10 seconds to set yourselves up to complete this diagram. And I'm going to switch to blue. These are not in your textbook, surprisingly. It's not really. Okay. Where's the next easiest place to do a field line? Yeah, I think on the outsides. I think directly on the outside would be the next easiest place. So if I drop the test charge right here, it's going to be repelled quite strongly by this positive charge. And then what's going to happen to it, or what's this one going to do to it? It's going to attract it for sure, but it's going to attract it pretty weakly compared to this repulsion because it's so much further away from the negative than it is from the positive. So if I combine those two forces, I would find that the direction of the force anywhere over here would be to the left. Now, I am assuming that these have equal charges on them, that this one has just as much positive charge as this one has negative charge. If they were unequal, this would actually still be true, but in other places, we have some asymmetry that I don't feel the need to get into. Alright, similarly, over on this side, we would have a field line that points directly in towards our negative charge, because any place that we drop a test charge, right, it's attracted to the negative, it's repelled from the positive, but the negative is way closer, so that kind of commands what the net force does. Alright, those are the easier ones. Follow-up questions from anybody about the three field lines that we have up there so far. Alright, I'm going to sketch on another field line and then we'll kind of evaluate it, but let me go ahead and directly get it right on. We're going to have a kind of curvy one right there and another curvy one down here. Those should be symmetric. I didn't do a fantastic job. So sketch those on and then we'll talk about why they look like that. Alright, I just dropped a test charge right here. The positive one repels it, kind of strong or kind of weak. Kind of strong, right? So it's very close. The negative one attracts it, kind of strong or kind of weak. Kind of weak because it's pretty far away, at least compared to that distance. So the field line would be in this, at this exact spot right here, the field line would be in the same direction as the net force, right? The combination of those two. We can graphically add those force vectors together if we add them head to tail. So if I kind of shift this one down to that head of this other one, right, the resultant would point like that, and that is exactly the direction of the field line right there. Okay? But then as we move test charges relatively further away from the positive and relatively closer to the negative, like maybe right in the middle. Why I switched to blue, sorry. If I dropped a test charge right here, the positive one still repels it, but weaker than before. The negative one still attracts it, but stronger than before. And those should be the same strength as each other. So if I add those head to tail, I should get something that points perfectly to the right. And then as I get closer to the negative one's more impactful than the positive. Okay, so we end up with that kind of curvy curve that points away from the positive and then towards the negative. And then everything else just gradually changes from this geometry to that geometry. Right, so I have something in between that would go like that, something that would be like that. Alright, I have something over here, something over here, and something here, something here. Right, so something kind of like that. And that's quite similar to what the one diagram on the top of, 568 looks like. These would match up together, and those would match up together. And these ones would match up also. Alright, so I went through that kind of fast, but I hope that you can appreciate why these original field lines are straight and why all the other ones are curved, because the force from the two charges creating the fields aren't, in alignment. Follow-up questions about this electric field? It's conceivable that I would ask you to recreate something like that. Alright, there's really two other types of electric fields that I'd like to do. I'll do a tiny bit quicker than that last one. And that would be if we have two similar charges that are quite close by. You want to do positive or negative first? Positive, alright. So we'll have a positive one here, a positive one here. Again, they'll have the same amount of charge on each other. It just complicates our lives if we do different amounts of charge. And I think, unlike last time, I'll put all the field lines on first, and then we'll take a look at a couple of spots afterwards. Alright. You do not need to do this dashed line. I'm just doing it to hopefully ensure that my diagram's neat-ish. What do we call that dashed line? Asymptote. Right? You all know about those, or just the IB math people know about those?
No, you don't know how to do.
All of you, right? Oh, that one over. Oh, that's actually pretty neat. Give you 10 more seconds to copy that down, and then I just want to look at a couple of spots and make sure that we can see that dropping a test charge yields, the geometry that we're seeing there.
Wouldn't it go straight to?
Wouldn't who go straight?
Wouldn't there be a line between the two protons or the two positives, but it would meet in the middle? It would
I don't think there'd be an asymptote there now. I could.
not an asymptote,
You're saying I
like
could do a field line?
Yeah.
I don't want to do that, but we could. I don't want to do it, but we could, and I'll revisit that. Alright, so first of all, let's do a test charge right here. I mean, that's the steepest curve that I see anywhere, so that's a spot we should care about. Alright, this charge repels our test charge pretty darn strongly, because it's close. And then this one repels it also, but not nearly so strong because it's far away. Right? So when we are close to an individual, when we're close to one of the two charges, that charge is going to dominate the field direction, but as we get further away, it becomes less dominant. So here, the field line points almost directly away from this positive charge. Not exactly, it's a little bit more vertical than that, but almost. When I go up here, okay, this one repels, it's not nearly as strong as here. This one repels, it's actually about the same as there. And what you can see is this one isn't so dominant anymore. The force from this other one, maybe it's half as much as that one, but now we really have to consider the combination of the two. And when we get super far away, the repulsion is almost identical from the two. So this field line becomes almost vertical. It wouldn't ever become exactly vertical, which is why we do have an asymptote. It's never going to actually reach that vertical line. But it comes ridiculously close, especially as we get further and further away. Over here, right, I think that's a pretty straightforward direction. This one repels it to the left. This one also repels it to the left. So the field has to point perfectly to the left. Let me comment on the field lines that Burton wants to put in. I'm not going to put them in, but I'll comment on it. Burton wants to put a test charge directly to the right of this. Okay, so this charge repels it to the right fairly strongly, and this one repels